What's up guys, welcome to another video. In this one I will be proving the beta gamma function relationship. If you remember in last video I used this equality without actually proving where it came from, so that's what I'm going to do today. I want to start with on one side gamma u times gamma v, and on the other I want to expand those using the integral definition of the gamma function. So gamma u is, let's use t to the u minus 1 e to the negative t dt, and we have another integral 0 to infinity, this time gamma v. I'm going to use s for the variable this time, s to the v minus 1 e to the negative s ds. Now because this is an integral with respect to t, and in the end it's just a number with respect to u, right, gamma u, I can slip it inside the integral on the right because this one is with respect to s, so it's completely independent of s. So this is going to transform our right hand side into a double integral. I can draw an integral, that is. Double integral t to the u minus 1, s to the v minus 1, e to the minus, and here we're going to get e to the negative t times e to the negative s. Because of exponent laws, we can add those up, and I'm going to factor out the negative sign. So we're going to have e to the negative quantity t plus s and dt ds. Now here I want to do a substitution, a couple substitutions that is. We're going to let x be equal to t plus s, and we're going to let y be equal to t over s. Now the t plus s substitution makes sense, right? You can see it right here in the exponent. T over s one doesn't make as much sense, but just trust me, I found that this works best. So both of those statements imply that we can find t and s with respect to x and y. How would we do that? Well, from this equation we get that t is equal to s times y, and then we can substitute that in this equation up here. So we get x is equal to s times y plus s, factor out an s, and divide by 1 plus y. We get that x over 1 plus y is equal to s. Now again, from this statement here we get that t is equal to s times y, so we can just multiply s here by y and we'll get what we want. So t is equal to xy over 1 plus y, and let's simplify this a little bit more. We have x times y over 1 plus y. I can add 0 in the numerator here and it won't change anything, so I'll do plus 1 minus 1, and we can split the fraction right here. So we have x times y plus 1 over y plus 1 minus 1 by y plus 1. This obviously goes to 1, so overall this is x minus x over 1 plus y. And this will become a bit more useful when we do the Jacobian matrix. The next step we want to do is figure out what dt ds becomes, right? What does it become when we change to x and y? Well, it becomes the determinant, the absolute value, that is, of the determinant of the Jacobian matrix times dx dy. Right, times dx dy. Now this matrix here looks like the partial derivative of t and s with respect to x and y. And if you've never seen this notation, let me expand it out for you. First we're going to get these two. So partial t with respect to x. If we take the partial derivative of t with respect to x, we get y by 1 plus y. Here we get, in this spot of the matrix, we get partial t if y is the variable, which is why I wanted this form. It becomes x over 1 plus y quantity squared. Here we have our dx dy. And in the bottom two spots of the matrix, we get these two. So the partial derivative of s with respect to x is simply 1 by 1 plus y, and here the partial derivative of s with respect to y is negative x by 1 plus y quantity squared. If we take the determinant of this, we now get the cross product here. So we have negative xy over 1 plus y quantity cubed minus x over 1 plus y quantity cubed, absolute value of this dx dy. Now, because x and y are strictly positive, we can see this because they're dependent on t and s are strictly positive. So because they're strictly positive, negative xy has to be negative, and when we take the absolute value of this, it becomes xy, and likewise for this negative sign here, it's going to go away and become a plus. Since both fractions have a common denominator, we can add those up and factor in x, which is overall going to leave us with dt ds is equal to x over 1 plus y squared dx dy. And we now have the double integral from where to where actually? Well, it's easy to see for x that as t and s range from 0 to infinity, x is also going to range from 0 to infinity. But it's a bit trickier for y. Although, if we look at t over s here, as t and s range from 0 to infinity, we can actually get every single value from 0 to infinity. You can see this, say t approaches 0 and s approaches infinity. We get 0, this is the minimum possible value, and if t is equal to infinity and s is literally anywhere from 0 to infinity, then we approach infinity, which is, well, the max value. So we have, again, a double integral from 0 to infinity, and we can replace t and s with their respective substitutions. So we have xy to the u minus 1 over 1 plus y to the u minus 1 times s, which becomes x here to the v minus 1 over 1 plus y to the v minus 1, e to the negative t plus s is x, so e to the negative x, and dt ds, as we said earlier, becomes this junk. So x over 1 plus y quantity squared dx dy. A bunch of simplifications here are possible. First of all, this x will cancel out this negative 1, and we are left with the double integral from 0 to infinity of, I'll put everything which has an x kind of to its side, so we have x to the u minus 1 times v, so x to the u plus v minus 1. The e to the negative x can also come here, and then we have y to the u minus 1 all over 1 plus y to some power. Now what is that power? It is u minus 1 plus v minus 1, so u plus v minus 2 plus 2, so just u plus v dx dy. Now we're going to do exactly the reverse of what we did in the first step, which is to notice that this inner integral here is with respect to x, meaning anything as a y can be held constant, so we're going to slip it outside of the inner integral. So we have y to the u minus 1 over 1 plus y to the u plus v dy times the integral from 0 to infinity of x to the, and I'm going to put parentheses here, you might see why in a moment, e to the negative x dx. Now recall that on the left hand side we had gamma u, gamma v, so I can write that again. Gamma u, gamma v is equal to this. You may not recognize it yet, but it's the beta function evaluated at u and v, and I'll prove to you afterwards. And this, well, it's gamma of u plus v. We can see this here. If we go back up, the integral definition of the gamma function of u is, you just put a u here and you have minus 1. In our case, we have u plus v. This implies that if I divide by gamma u plus v on both sides, because it's not equal to 0, we have beta of u plus v equal to gamma u, gamma v over gamma u plus v. And this is precisely what we set to prove. If we go back up, this is what we want. Now, however, let's tackle this. This is not the form of the beta function I showed in the previous video, so that's what I'm going to do next here. I'm going to rename the variables first. So we have the integral from 0 to infinity of t to the u minus 1 over 1 plus t to the u plus v dt. And the first thing I want to do here is do a substitution of letting t be equal to the tangent squared of x. This might seem weird, but it works out. That implies upon differentiation that dt is 2 tangent x secant squared x dx by the power rule and chain rule, and we can substitute everything in. So we have the integral, actually, as t approaches 0, x needs to approach 0, and as t approaches infinity, tangent x has to approach pi by 2. I'll take this 2 here from the dx outside, and now we can replace everything in. We have t is tangent squared, so we have tangent squared. Well, I'll combine the powers here, so tangent to the 2u minus 2 of x over 1 plus t is tangent squared x, quantity to the u plus v. Dt here was, well, the 2 is outside, so we have tangent x secant squared x dx. Now this tangent x is going to add 1 to this power, so it's just going to be negative 1. And we'll be left with twice the integral from 0 to pi by 2. Now notice that here, 1 plus tangent squared is secant squared x, and that means we have secant to the 2u plus 2v. If we combine it with this secant, we're going to get tangent to the 2u minus 1 of x times secant to the 2 minus 2u minus 2v of x dx. Now I get this is a really weird power, but now the trick is to express everything with sines and cosines. So I have the integral from 0 to pi by 2 of tangent is sine over cosine, so sine to the 2u minus 1 of x over cosine to the 2u minus 1 of x. Secant is 1 by the cosine, or alternatively cosine x to the negative 1. So we can just flip the signs of everything here. We're going to get cosine to the 2u plus 2v minus 2 of x dx, and now we can simplify with this. So we have twice the integral from 0 to pi by 2. Well, the sine doesn't cancel with anything, 2u minus 1 of x, times the cosine, and we have 2u, because it's a division, we have minus 2u. The v stays, and we have minus 2 minus minus 1, so minus 1 of x dx. And this is exactly what I showed in my last video. This is the beta function of u and v in its trigonometric form. So we just proved that this is the beta function, and thus that this whole thing holds. I hope you enjoyed this video. If you did, please make sure to leave a like and subscribe, as it would really help me grow. Sharing the channel also would help tremendously. If you have any questions or any integral or problem recommendations, please make sure to leave them in the comments, and I'll see you in the next video.